Okay, did you have any questions on anything that we did last week? I guess what we'll do then, we'll start on page 61.
Professor, quick question.
18.
The quiz is going to be everything we've learned up until this afternoon?
Yeah, it'll cover today's material. And we'll be back in a couple of sections. Can't cover too much in 4 questions. Okay, on 18, then it says, find one example of each of the specific shapes in the following figure. Assume that they appear, if they appear to be right angles, they are right angles. If they appear to be parallel, they're parallel. And if they appear to be congruent, they're congruent. So, A, do you see a rectangle? Now, a rectangle is defined to be, remember how a rectangle is defined?
A square can be a rectangle, but a rectangle can't be a square.
Yeah.
Okay.
Rectangle says all angles are right angles.
I see.
So the BDFH will work. Do you see a kite? Okay, say it a little louder, Bailey.
BCDG.
Okay, you see it, BCDG. Okay, then an isosceles triangle with no right angles.
DEJ.
Okay, DE.
Unless that's a scalene.
Okay. OD. ODE. Now, an isosceles has to have
Yeah, like
Two equal sides.
two sides are equal. What'd you say, Bailey?
Yeah, like DGD, CBD,
Okay.
AG.
And it could be any of those equilaterals, right?
Yeah.
Like BCD, is that what you said?
Yeah, BCD.
Yeah.
I forgot that rule.
Two sides have to be equal. It doesn't say anything about if there's 3 sides. 3 sides the same would be the same as an isosceles. So an equilateral,
CAD.
okay, BAG, there's about 4 of them in there, right?
2, 3, 4, 5 altogether.
Okay. There's a right isosceles triangle. You see it? I think there's just one. If you go into that right bottom corner, you see EFI.
Oh, yeah.
It's a tough one to see. So right scaling. There's probably a bunch of those. No sides equal, right? You said AHB? Is that what you
Yeah.
said? Yeah, I mean, there's at least 4 of them in there. Parallelogram that is not a rectangle.
You got to be the same as the kite.
Yeah. E, G, yeah, you could do that. Okay, an isosceles trapezoid. It's in that bottom, it's in that bottom part. BD is one base, AE is another base, and you see AB and
Yeah.
DE are the isosceles part.
A, B, D, E, A,
Mhm.
B, D, E, yeah.
Do you see it?
Yeah.
An obtuse scalene triangle, so none of the sides are equal, one has to be an obtuse angle. You said D,
J.
Mm-hmm.
E, okay. Or one that's a little bit more obvious is a D, I, E, right?
Definitely.
That's
Oh, yeah.
okay. J, trapezoid that is not isosceles. Okay, you said G, H, and BD. Okay, that'd be one. Or you could get an AF and then a BD or some other mixtures there. The bases cannot be the same, but you have to have parallel sides. A pentagon. Now, this is not saying anything about an equilateral. It's just a five-sided figure.
Sure. B, C, D, F, H.
B, C, D,
D, F, H. That's a pentagon. That's a
okay. And there's some other ones in there.
Oh, yeah.
All right, so you got the idea. Now, 20, you can look at that if you want to. I just tell you for A, there's 18 of them. If you're curious in looking, B is 3, C is 2, and D is 29. It's a little bit too time consuming. 22 says those are equally spaced points on the circle. And how many different rectangles can you draw using 4 of the points of the circle as vertices? If you start out with A, B, E, F, right? And then you just go around the circle, like B, C, and then F, G. So you could do one with A, one with B, one with C, that'd be 3, 4, D, 5 with E, 6 with F. I don't think I've duplicated any. And G, but you can go around that thing, and you can get 6 of them. I think I'm duplicating some. You go A, B, C, D. Once you get to E, you're duplicating. So 1, 2, 3, 4, and then if you split them, if you go AC,
Mhm.
and then you go BD, and then you got 6 of them, and that's how many there's got to be. And then it says how many different trapezoids can you draw using the 4. Well, there's 16 of them, but they're not too bad to get. If you use one parallel side BC and the other one AD, so it'd go A, B, C, D. Then if you just take that A and rotate it around, right? So that you go A, C, D, E, C, D, E, F. So that base point of that trapezoid, and it just go around and go upside down, so you can go around the whole thing. So you'd have 1, A would be 1, B would be 2, C would be 3, D would be 4, E would be 5, F would be 6, G would be 7, H would be 8. And now, when you're back to A, that trapezoid is upside down. So you can go around again. You see what I'm saying? And then you go around twice. Then you could go back and do an A, B, D. You could have A, E, and B, D. And you could go around that way. But you'd have 16. And then the C part of those 16, all of them are isosceles. Now those cutout things, you can do them. So 28, and, well, they're just saying how do you fold it and cut it out. So I'm going to skip over to 28. And it says that does the rhombus shown have reflection symmetry? No, this is the one that has to have an axis of symmetry to it. I didn't get the sides equal. I'm just going to go to the next page and do, because all 4 sides have to be equal on a rhombus. They get very close, pretty close. So, does a rhombus shown have reflection symmetry? So it has to have an axis of symmetry that it spins around on and falls back on itself. So can you see? You see a reflection. If you draw a dotted line through there, that you'd fold it around. Okay, it'd reflect around that, right? What would be the other one? Yeah, be down this way. Now, there wouldn't, it wouldn't be any others. You couldn't, if you did try to do something like this, when you fold it around, it wouldn't fold back on itself, right? Then it says, so it has two. So A is 2. And B, does the rhombus have a rotation symmetry? And that would be a dot, like a point that you'd rotate it around and then it'd fall back on itself. And there aren't any. Just for example, if we did a square, the center of that square would be a rotation. If you rotated that 90 degrees, it would just fall on itself. So if you lettered this A, B, C, D, you could rotate it 90 degrees and put C here and D there and A there and B there. Then you could rotate it again and rotate it again. And some things have rotation symmetry, but that rhombus doesn't. Okay.
How does it not have one? If you rotate it 180 degrees, doesn't it fall upon itself? When A go to C and C go to A, then D would be switched to.
If you went 180,
Yeah.
okay. Oh, you're right. It does have one. Thanks. You're right. Thanks. Okay. So 30. So this triangle, it's an isosceles. So okay. So does the right isosceles triangle shown have a reflection symmetry? And if so, okay, so how would you draw it?
From the right angle to the hypotenuse.
Okay, so perpendicular, just, right? But that would be, this would be 90 degrees. Any others? So this would just have one. And then the B part. Does the right isosceles triangle have a rotation symmetry? Okay, you said if you don't see one, that's correct. Okay. And we'll look at this next chapter. These tessellations that they're talking about on page 65, if you notice down there they say tessellation or a tiling. So it's a polygonal shape that you can, well, you can arrange it so that they're talking about a countertop that lays flat on the countertop and it doesn't overlap, but it covers everything. And that's called a tessellation. And not all polygons are able to do that. I'm showing you on page 66 a couple of tessellations. And then they're showing you the theorem 2-1 angle measure of a triangle. We all know that the interior angles of a triangle are 180 degrees, right? Some of the angles is that. And they're showing you how they derive that. And then on the next page, they show you how the polygon, they get the formula for the polygon, and they just draw lines between vertices of the polygon, and then they have triangles. And then what it turns out to be is that measure of the angles of a polygon then, or that has n sides, is n minus 2 times 180. So, you know, like a triangle has 3 sides, so 3 minus 2 is 1, so that's 180 degrees, and then it has more sides than that. Then they're going to talk about a regular polygon, and that's where the sides are all equal. So this polygon formula is for any polygon. It's not a regular one. It holds for regulars, but it's any polygon of whatever number of sides. That's what the interior angles are. But a regular pentagon, a regular hexagon, a regular octagon, all those sides are equal. So then what you do is the vertex angles, if it's regular, you just divide it by the number of sides. So it's the formula for the angles of a regular polygon, the measure of the angles, interior angles of a polygon of that many sides, and then you divide it by the number of sides. And that tells you what the angles of the regular polygon are. Then they give you on page 69, you know, if it's 3 sides and it's regular, 60 degrees, that's a triangle. 4 sides, 90, 5 sides, 108, and so on. They've just divided it out and given it to you as a table. And then on page 170, they're showing you a regular tessellation. So it's a regular polygon. And not all polygons are going to be tessellations. And what it has to be is where those points meet in a tessellation. When you have a tessellation and it's a mapping, the sum of those angles has to be 360 degrees. So wherever those sides meet in a point, then the sum of those angles have to be 360. So not all polygons or regular polygons are going to be tessellations. And they're telling you in there that so they say if you look at the table 2-1, the ones that can form tessellations are one whose, if they're regular polygons, are ones whose angles are factors of 360. So they say like 60 degrees, which is a triangle, is a factor of it. So you form a tessellation by putting those equilateral triangles together. Rectangle, 90 is a factor of 360. So you can put four-sided figures together, but you can't put five-sided figures because that 108 is not a factor of 360. So you can't form a tessellation. Six-sided figures at 120 is a factor of 360. So six-sided figures can form a tessellation, but 8 cannot because 135 is not a factor of 360. So that's, if you see it there in that paragraph right above the box on the bottom of the page, it's kind of explaining that to you. Okay. On page 71. Now, it says make 6 copies of the following triangle and show how they can be used to create a tessellation. I guess I'll leave that one and 4 if you want to look at them to see how that's done. That would be too hard to give a question on, so I wouldn't. But for mind games, you can look at that. Now 6 is a problem where it says you have to use a protractor and measure the angles on the sides. So we're not using a protractor, so that's just not something we're going to do. 8. And it says the measures of angle ABC are given. Can you make a triangle ABC with the given angle measures and explain? So A, generally, what would have to happen to be able to make a triangle ABC with those angles? It's just a general concept of it. What would the sum of those 3 angles have to be?
180.
So all you do is you look at them and say, do they add to 180?
Yes.
What's that?
So A does.
A does, don't it? So you can make a triangle with that. B is no. And C is no, right? I mean, once you see it, it's just it's pretty simple. Now, that number 10 is kind of an interesting thing to, it's going to be difficult to try to make something. I'm sort of tempted to do it. Is that pretty good? So that when they put like those two, it means that one is equal to, where's the other one?
On the very bottom,
Yeah,
bottom right.
so those two are equal. And it's saying this one equals this one. And then this one is supposed to be a right angle. This is supposed to be 95 degrees. That's 80, isn't it? This one they call E. They call this one B. 20 degrees. They call this one A. They call this one 65, right? This one they call G, down here. Then they say, calculate the measure of each lettered angle. Congruent angles and right angles are indicated. Well, A should be reasonably easy, shouldn't it?
A should be a 45,
Yeah, yeah,
should be.
yeah. So this is 45. This is 45. And then could we figure out G by calculating this angle? That angle would be 180 minus 65, wouldn't it? What would that be? 115? So then you'd add 115 and 45, subtract it from 180, right? So that's 160. That's 20, right? Is that right?
20's right.
So we got A and G.
Find B.
Okay. So how are you going to go about finding B?
Well, the angle would be 115 again.
Okay, so this one is 150. So then B equals,
180 minus 115 minus 115 minus 20.
yeah, 20 plus 150. So that's 135. So is that 40 something?
35.
we got E to figure. We could get that angle, right? That's 85. Now, if we could get this angle right here, we'd have E even.
You can get it. We have G, we have the angle right below it.
How do you got the angle below it?
From F, which was 70, G is 20. Wait a second. How did I get that? Just like my theory.
Well, could you get this angle right here?
H is 55.
Where you,
Because you have the 80, we know the 45 right beside it, the adjacent angle is 45. 80 and 45 leaves 55, that's H.
okay, so that blue angle right there,
Yes,
is, you know, you want to call it H?
it's called H in the book, sir.
Oh, is it?
Hmm?
It's 180 minus 45 plus 80, right?
Minus 80. Yes, right, you're right, you're right. You're right. 55.
That's 55, isn't it?
Mhm.
So we were supposed to get that one, huh?
Yeah.
We can figure out
D is where?
it is the angle next to E.
Oh, okay, D. D is right here.
So on the opposite angle 65, and then you can take 180 minus B from it.
So you can figure this one. Is that what you're doing?
You can down 65 because that's the opposite of it.
Okay.
And then you can figure out the other angle from taking 180 minus B, and then you get 135.
135.
That's all equal to 60.
So then n minus 2 times 180. So that would be, let's see, 4 minus 2 times 180. That's the interior angles of this four-sided figure, right? That's 360. And then you'd subtract the sum of 65 plus 135 plus 80. Is that right?
Yes. And it comes out to 80.
80. So D was 80. So we got E. Was there an F and a,
There is an F.
There's not.
where's the F at? F was here, wasn't it? Well, that we can do,
Yeah, that's easy. 90 minus 20.
Right.
7.
okay. It's 180. Oh, oh yeah, 90 minus 20. Okay, that's the easiest way to do it. 70. E, F. So this one, F. So we got A, B. Was there a C in there that we figured out?
Yes, C is equal to the other angle
Where is C at?
up top.
Yeah.
Top right.
Oh, it's this one right here.
Yes.
Seeing how that's congruent to the other angle, and we know that G angle, G plus the 30, so we know there's 130 left, which we split, 65 apiece. Those two equal angles.
I'm not seeing how you're figuring it.
So I got C to be 45 degrees, but
This,
E be 50 degrees.
this right here is 30,
Yes.
right?
Yeah, that's 30.
30. So therefore, this angle, 30 and 20 is 50, leaving 130 to split between these two equal angles. They have to be 65 apiece. So there's one angle, this big triangle, which is 50,
So this angle, you get it
that's
by
30.
taking 180 and subtracting 55 plus 95.
25, 55, leaves 30.
So it's like 180 minus 2 minus
So this,
50.
and this, was this did this have a letter on it?
No,
Okay. So this is just a 30-degree angle.
right, but we need that to get this angle.
Yep.
Okay.
And that leaves these two.
180 minus.
So you're taking this to get C,
180 minus
2
50.
times C
Right,
plus 50 degrees
right,
has to equal 180.
right, exactly.
Because these two are the same. 2 times C plus 50. So 2C equals 130. And C has to equal what? 65? So then C is 65. So now this is 65, right?
Yes.
Right,
So then E has to equal 180, because there's 180 degrees in that triangle, minus
150.
the 85 plus 65. And that, is that 30?
Yep,
Okay. Did we get it then?
Yes.
Those kinds of problems are kind of interesting to do, I think. All right, 12. It says find the missing angle measures in the quadrilateral shown. So A,
quads always equal 540.
so it's, yeah, the formula is n minus 2 times 180. So it's 4 sides minus 2 times 180. So that's 2 times 180, so you got 360.
Okay, understand.
So you want to always go back to your formula. So each one of those 4-sided figures has 360 degrees in it. So then what you got is you got 360 minus, you got two 90-degree angles, right? And you got 108. So you got 180 plus 108. What is that? 288? Is that right? Sometimes I can't add, subtract, multiply. Fine. So it's 2. Is that 72?
Yes.
So B would be 360 equals. In this one, you just set up an equation. You got 2 times 90 plus 90 plus x plus 15 plus x, right? So you'd have 360 minus 180. I just multiplied that, subtracted, right? Equals 2x plus 15. So this is 180 minus 15. So x is going to be what? This is 165 over 2. Is that right? Did I subtract right? 180 minus 15 is 165, isn't it? 82 and a half.
75 degrees between.
Okay, what did I do wrong?
So you have your equation 2x plus 15 plus 180 is what it goes down to, and then you just divide 2 from the 2x and then divide that from, and then divide 180 by 2, getting x plus 15 equal 90, and subtract 15 to isolate the x. And
So what's wrong with this one?
I don't know.
It's 360 minus 180, isn't it?
Yes.
That much is right here. This is right, isn't it?
Yeah, that's right.
Then you subtract the 15.
You just, okay. Yeah, you subtract the 15 from it.
And that's 165, isn't it?
Yeah, I did something wrong.
Then divide by 2,
Yeah,
82 and a half. I think that's right.
Mm-hmm.
yeah. I did something wrong.
C is pretty straightforward. D would be a little bit, let's look at D. Does it seem,
Professor, why is C straightforward? How do we know those C angles are congruent?
where you,
12C.
what, oh. They're just telling you.
Okay?
That's what they're doing. So you just go 3Z, right?
Okay.
I guess C would be 360 equals 3Z plus 120. So 3Z would equal 240, and Z is going to be 80. And the other one, you're just going to have to go, y minus 34. It's equal to 360. Y minus 34 plus, and we don't have to worry about brackets because we're not subtracting. We're just adding all these things. Y plus 2, and that's all equal to 360. And then calculate it out. Well, I'm past due on you.